The 10th of May, 1940. Winston Churchill addressed a cabinet that had not yet finished its first cup of tea when the teleprinters began screaming. Germany had invaded France, Belgium, the Netherlands, and Luxembourg simultaneously. Within 6 weeks, the British Expeditionary Force would abandon 84,000 vehicles, 2,500 guns, and 400 tanks on the beaches of Dunkirk. But the numerical catastrophe concealed something far more dangerous than lost equipment. Britain possessed approximately 2,200 tanks capable of engaging German armor in open battle. Germany fielded 3,500, with production lines turning out 200 more every month. Yet the numerical disadvantage was only the beginning. The deeper crisis was metallurgical, invisible, and almost impossible to solve. Every high-quality tank track link in Britain depended on a single manufacturing process that had been perfected, patented, and industrialized almost entirely in Germany. The moment war was declared, that supply chain became an enemy asset. The component was manganese steel track, and the problem was extraordinarily specific. Ordinary steel shatters under the repeated impact of 30-ton vehicles crossing rocky ground, frozen soil, and shell-cratered terrain. Manganese steel work hardens under impact. The more punishment it absorbs, the tougher its surface becomes, whilst its core remains ductile enough to resist fracture. The Germans had mastered the alloy composition, the casting temperatures, the heat treatment sequences, and the quality control procedures over 2 decades of continuous development. British manufacturers attempting to reverse engineer captured samples in the summer of 1940 produced track that lasted 200 kilometers before catastrophic failure. German track on equivalent vehicles lasted 3,000. The mathematics of armored warfare were simple and brutal. A tank with broken tracks is a pillbox. A pillbox cannot advance. You cannot win a war with pillboxes. The War Office calculated that equipping the Churchill, Cromwell, and Valentine tank programs through 1943 would require 47 million individual track links. Current British production capacity, using the inferior processes available domestically. 0 links per month that met operational standards. Every qualified metallurgical engineer who understood high manganese casting at scale was either German, working for German subsidiaries, or had learned their trade from German instructors. The expertise was geographically and politically inaccessible. General Frederick Pyle, commanding Anti-Aircraft Command, summarized the situation to the Ministry of Supply in a memorandum dated July 1940. "We are attempting to build an armored force without the ability to keep it moving. The tracks wear out faster than we can replace them. This is not a supply problem. It is a knowledge problem, and knowledge cannot be requisitioned." His name was Leopold Joseph Schultz, born in 1887 in Düsseldorf, in the Rhineland, to a family of ironworkers. His father cast decorative railings and structural brackets for the buildings rising across industrial Germany. Leopold grew up understanding metal not as an abstraction, but as a physical reality with grain boundaries, thermal expansion coefficients, and a personality that changed depending on how quickly you cooled it. He left school at 14, worked in his father's foundry for 3 years, then discovered an aptitude for athletics that redirected his life entirely. By 1908, he was a competitive middle-distance runner, representing his athletics club in regional competitions across the Rhineland and Westphalia. He was not a champion, but he was relentless, the kind of competitor who studied the mechanical efficiency of his own stride, the way an engineer studies tolerances. It was this analytical habit that brought him to cycling. He was 22 when he first examined a bicycle chain with professional curiosity and noticed what experienced cyclists had simply accepted, that chains stretched unevenly under load, that sprocket engagement degraded progressively, and that the failure mode was not breakage but cumulative deformation that no amount of lubrication could prevent. The problem was the metallurgy of the link pins. They were too soft. They deformed plastically under the lateral forces of gear engagement, imperceptibly at first, then catastrophically. Schultz spent 18 months in evenings and weekends experimenting with pin hardening processes in his father's foundry. He developed a differential hardening technique, a hard outer surface achieved through controlled carburization with a tough core preserved by precise quench timing that extended chain life by a factor of 4. In 1912, he filed a patent. In 1913, he founded a small manufacturing concern in Essen to produce the improved chains commercially. The Great War interrupted everything. Schultz served as an infantry NCO on the Western Front from 1914 to 1917, was wounded at Passchendaele in circumstances that left him with permanent damage to his left knee, and returned to Essen to find his company had been absorbed into a larger industrial group during his absence, his patent assigned to corporate ownership, and his role reduced to that of a production supervisor in a factory making things he had invented for the benefit of men who had not. He resigned in the spring of 1919. He was 32 years old, technically brilliant, legally dispossessed of his own innovations, and entirely without capital. If he could not race, perhaps he could improve the machines. The thought arrived fully formed, almost consoling. What he could do was look at problems differently from men who had spent their careers inside a single industry. Working as a freelance metallurgical consultant through the early 1920s, Schultz began examining continuous track systems on the agricultural tractors, then proliferating across German and British farms. The track link problem was structurally identical to the chain pin problem he had solved a decade earlier, but geometrically more complex and operationally far more demanding. Agricultural tracks operated in wet clay, abrasive sand, and frozen ground, absorbing impact loads that no chain had ever experienced. The existing solutions, cast iron links, simple steel stampings, bolted assemblies, all failed progressively in the same manner. Surface wear exposing the softer core, then accelerating wear, then link failure. Schultz recognized the pattern immediately. His solution, developed between 1922 and 1924 and filed as a German patent in March of 1924, involved a three-stage manganese steel casting process. The molten alloy, containing 11 to 14% manganese, was poured at precisely 430 degrees Celsius into molds preheated to 650 degrees. The initial casting was then water quenched from above 1,000 degrees, rapidly enough to prevent carbide precipitation at the grain boundaries, slowly enough to avoid thermal shock cracking. The resulting links were then subjected to controlled impact treatment that initiated the work hardening process before installation, creating a pre-hardened surface whilst preserving core toughness. The result was a track link that lasted 8 to 10 times longer than competing products under equivalent field conditions and, crucially, could be manufactured with consistent quality once the process parameters were established and maintained. By 1928, his links were standard equipment on Hanomag and Lantz agricultural machinery across Central Europe. By 1932, following licensing agreements, he had negotiated with considerably more legal sophistication than in his younger years. Modified versions were appearing on early military vehicle prototypes in Germany, France, and Czechoslovakia. He had, without intending it, solved a problem that would become one of the central logistical challenges of mechanized warfare. He had solved it for tractors. When the British Army came looking for him in the autumn of 1939, he was 52 years old, living in Zurich, having left Germany in 1933 for reasons he never discussed publicly, but which required no explanation to anyone familiar with the period. The Ministry of Supply representative who met Schultz in a hotel near the Bahnhofstrasse in October 1939 brought with him a specification document, a memorandum signed by the Director of Mechanization, and an offer. The specification described production requirements that Schultz initially read as a typographical error. 47 million links. Delivery commencing April 1941. Facilities to be provided by the Crown. Workforce to be hired and trained by the recipient. Schultz asked for 72 hours to review the technical requirements, then sent a single-sentence reply. The process is transferable. The timeline requires exceptional commitment. Exceptional commitment was understating it considerably. The facility allocated to Schultz was a former textile mill in Coventry, emptied of its machinery and still smelling of machine oil and cotton dust when he arrived in January 1940. It had 14,000 square meters of floor space, a 32-ton overhead crane, and access to the Coventry electricity supply grid. It had no casting equipment, no metallurgical laboratory, no manganese supply chain, and no workers with relevant experience. Schultz hired Thomas Whitmore, a production engineer from a Birmingham foundry, as his operations manager, and the two men spent February mapping every single element of the process that would need to be built from nothing. The numbers were unforgiving. To produce 47 million links by the end of 1943, the facility needed to reach a steady production rate of 120,000 links per week by March 1941. That required 24 casting furnaces, 16 quench tanks, 8 impact treatment stations, and a workforce of approximately 2,200 people operating across 3 shifts. In January 1940, they had 4 furnaces installed and 47 workers. The math was brutal, and Schultz posted it on the wall of the canteen in handwritten figures where every worker could see exactly what was required and how far they were from achieving it. January, 8,000 links produced. February, 31,000. March, 89,000. April, 204,000. May, 388,000. June, 671,000. The exponential curve was real, viscerally real, felt in the heat of furnaces operating around the clock and in the faces of workers arriving for 6 a.m. shifts in blackout conditions with bombers overhead. By June 1940, 67% of the workforce were women, wives and daughters of men now in uniform, learning metallurgical quality control procedures that Schultz taught personally, working from handwritten manuals he produced at night. Margaret Hallows, 23, from Leamington Spa, responsible for temperature monitoring on casting line 7, later recorded in a factory journal that Schultz stopped beside her station one morning in April and said quietly, "Every link you pass tonight will be on a tank. Every link on a tank keeps a man moving. Moving men come home." She wrote, "I've never worked harder in my life than I worked after that morning." The military vehicle experimental establishment at Chertsey subjected Schultz's Lynx to qualification testing in September 1940. The specification required 5,000 kilometers of continuous operation across mixed terrain, including waterlogged ground, rubble, and graded stone, with inspection at 1,000-kilometer intervals, and no link replacement permitted during the test sequence. 3 competing manufacturers submitted samples. The first failed at 1,200 kilometers with 34 link fractures across a single track assembly. The second reached 2,800 kilometers before progressive wear opened gaps in the track engagement, sufficient to cause drive sprocket slippage. The third lasted 3,400 kilometers before thermal fatigue cracking became structurally critical. Schultz's Lynx completed 5,000 kilometers with no fractures, no thermal cracking, and wear measurements within 4% of original tolerances. The results were not close. Contract WMV 1940-447 was awarded on the 18th of October 1940. 47.3 million track links, delivery schedule running from January 1941 through December 1943, at a unit price of 3 shillings and 4 pence. Total contract value, $7.9 million. Production targets, to be monitored monthly by Ministry of Supply inspectors, escalated on a schedule that Schultz himself had specified as achievable and had already demonstrated was being met. The combat validation arrived from North Africa in the autumn of 1941. Lieutenant Colonel Arthur Mayfield, commanding the 6th Royal Tank Regiment in Operation Crusader, submitted a maintenance report in December 1941 that circulated within the War Office under a restricted classification for reasons that, in retrospect, seem unnecessarily cautious. Prior to re-equipping with Schultz processed tracks in October 1941, Mayfield's regiment had been replacing track assemblies every 600 to 900 kilometers of operational movement. Track failure was consuming 30% of maintenance hours and was the primary cause of tanks being rendered non-operational before engagement. After re-equipping, 0 track failures due to link fracture in 2,200 kilometers of operational movement. Maintenance hours attributable to track systems fell by 71%. Operational readiness rates increased from 58% to 84%. The difference, Mayfield wrote, is the difference between an armored regiment and an armored regiment that can actually fight. German military intelligence acquired 3 example links from captured Valentine tanks in Libya in early 1942 and sent them to the Heereswaffenamt Metallurgical Laboratory in Berlin for analysis. The translated summary of the resulting report, recovered from Wehrmacht archives after the war, acknowledged that the links demonstrated manganese content and microstructure consistent with a sophisticated 3-stage casting and treatment process. The report noted that the work hardening depth, the grain boundary characteristics, and the carbide distribution pattern indicated process control of a standard that German military production was not currently achieving at scale. It recommended urgent investigation of domestic manufacturing capacity. That investigation found what the British Ministry of Supply had also found in 1940. The expertise required was concentrated, specialized, and not easily transferred. German tank production facilities were, by 1942, facing their own raw material pressures. Manganese ore imports from the Soviet Union, which had supplied 40% of German requirements before June 1941, had ceased entirely. The window for catching up had already closed before the report was filed. The strategic bombing campaign against German armored vehicle production facilities between 1942 and 1944 cost RAF Bomber Command 2,100 aircraft and 14,700 aircrew killed or captured over targets, including Kassel, Schweinfurt, and Friedrichshafen. The attacks were costly, partially effective, and ultimately insufficient to collapse German tank production, which peaked in 1944 at 8,300 vehicles despite sustained bombardment. German engineers adapted with underground facilities, dispersal to smaller workshops, and accelerated use of simplified components that sacrificed quality for volume. Whilst those bombers were dying over German cities, the Coventry facility was producing 900,000 links per month with an operational reject rate of 0.3%. The irony required no editorial comment. The nation that had spent 20 years perfecting the process was bombing factories. The nation that had learned the process from a single immigrant engineer in a former textile mill was producing superior components in quantities that no strategic bombing campaign could threaten. Leopold Schultz died in Coventry in February 1953, aged 65, of pneumonia complicated by the lung damage accumulated during decades of foundry work in incompletely ventilated facilities. He held 14 British patents at the time of his death, all assigned to the Crown under wartime agreements that he had signed without visible resentment and apparently never sought to renegotiate. The Coventry facility he had built from a cotton mill was by then employing 3,800 people and producing track components for the new Centurion tank program. Thomas Whitmore, his production manager, spoke briefly at the funeral. "He told us once," Whitmore said, "that metal remembers everything done to it. He meant the heat treatment, but it seemed to apply rather more broadly. The technology descended directly from Schultz's 1924 patent today underpins armored vehicle track production across NATO member states, with combined annual output exceeding 200 million components from facilities in Britain, the United States, France, and South Korea. The differential hardening process, the manganese specification range, the quench temperature parameters, all are traceable through documented engineering lineage to the processes Schultz developed in the evenings and weekends of a dispossessed consultant working from a Zurich apartment between 1936 and 1939. Germany, which had dominated high manganese casting technology from the 1890s through the 1930s, produces fewer than 3% of global armored vehicle track components today. The nation that entered the war with zero capacity and an immigrant engineer and a cotton mill now supplies the alliance that defeated it with the technology required to keep tanks moving. German engineering, in this particular contest, came in second place.